And welcome to SanfordFlipMath. We are in PreCalculus, working through the Demana Waits Foley Kennedy PreCalculus book. We are in Chapter 8, kinda. And as you may recall from other videos, we're actually pulling a lot of the material from our Algebra 2 book, which is the Glencoe Algebra 2 book, somewhere around 2010 or 11-ish. No, probably 2008 copyright. And this is what you're seeing here is an image from the supplementary materials. So anyway, we're going to finish up our look at conic sections. Well, technically there'll be one more video on this where we kind of do a little mix and match, but we're doing our final installment in terms of different shapes, the hyperbola. And I just want to remind you again, when we're talking about definitions, geometric definitions, they all sound like the set of all points in a plane, blah, blah, blah. And the rest of it's about distances. So equidistant to a fixed point, a fixed line for a parabola, equidistant to a fixed point called the center, such that the sum of the distance to two fixed points is constant. And then here we are talking for hyperbola. We're still talking about two distinct points like we did for ellipse, but now we're talking about, instead of sum, it's different, and it ends up being amazingly different in terms of how the thing actually ends up looking. And so what I'm going to do is kind of sketch in what hyperbola looks like, and it actually has two branches, two chunks to it. So something like that. And so again, the concept here is that if I take and measure from a point on the hyperbola, excuse me, this distance and this distance, whatever those two distances are, if I subtract them, I will get some number. And then if I do that from some other point, okay, it could be right here. If I measure that distance, I'm going to call this D1 and D2, and I know I've mentioned in class, and maybe I did in the other video. Technically, I mean, these are red distances now, and so these two values are different from those green values. Okay, but their difference is that same constant. Okay, and just one more for kicks and giggles. If I picked one over here, and it doesn't matter which branch, if I subtract this minus this, D1 minus D2, I will get the same constant. Now, there's even one more catch here. You probably are looking at this going, now obviously this distance is longer than this one, so when I subtract it, I'm going to get positive. Whereas here, when I subtract this distance minus this one, it's going to be negative. So the only catch is these really need to be absolute value, just so we're talking about a positive distance or difference, positive difference. Okay. All right. So this is an illustration of the geometric definition for hyperbola. Now, I'm going to take just a second, like I've done in the other shapes, except for circles, to talk about applications, because shapes, applications for circles, they're just endless. And I do want to thank Mr. P, whoever Mr. P is, Mr. Pleacher, I would imagine, for these fine images. Here is a hyperbolic image. This curvature is following that same pattern, and so somewhere up here would be a focus, and there's an imaginary second branch to this somewhere. This one I think is actually pretty sweet. I mean, any of them are sweet. You may or may not be able to see it in the video, but the light cast, and I don't know if you can see that little symbol track, and it's not letting me draw on here. I don't know why not, but and then there's another one down here. So these are both from that light, the lampshade, so that the way the image is being shot up against that flat wall. These are hyperbolic in shape. They're gears intertwined. Pretty cool. I didn't know this. The sonic boom, the shape coming off of the back of an airplane. So here's a cone. Well, this makes sense really, because the cone is coming off the plane that's going at the speed of sound. And then if this is a flat surface down here, that slices that cone in the shape of half of a hyperbola. Okay. All right. Well, that's enough of that. Oh, that's kind of cool. So we have the shape of the nuclear power plant, kind of like down near Lake Erie. So cool stuff. Okay. Let's pop back and get some work done. All right. So how does this end up looking? Well, it looks very, very, very much like the equation of an ellipse. The only difference is, pardon the pun, it's difference. So for ellipse, the sum is constant. For hyperbola, the difference is constant, and the equation looks just like ellipse, except it's a difference. Okay, now there are some distinct issues that will come up because of, as a result of all of this, but in terms of the standard form for the shape, it is the same except for that difference. Now, a couple other little issues here. Back to Old Faithful here. C is the distance to the focus, as it was for ellipse, but at least this looks exactly like the Pythagorean theorem, so that's comforting. Okay. Now, the other thing that you need to know too, for an ellipse, a squared is the bigger one. For hyperbola, a squared is the one that's with the positive term. Okay, so notice this time y actually came first because it's positive, whereas this one, the negative is in front of the x squared. Okay, this one, same idea, only it's the x's are positive. So for hyperbola, not that it really matters as much, but the a squared always, the a is always with, or the a squared is always with the positive term. Now, the thing that'll be less fun is we have asymptotes. And we'll see that when we go through the whole process of doing the graphing. And it starts out looking like we're going to graph an ellipse, but then all of a sudden we go psych, and it's just a little different. Okay, so again, as is normally the case, I would recommend doing this side and maybe this, but you got to kind of watch things a little bit, and we'll talk about how this all works, and we'll talk about what transverse and conjugate axes mean and all that kind of stuff. Okay, all right. So let's start out by just kind of doing an example. Okay, so because of the minus, this is a hyperbola, and as you may recall from doing ellipse stuff, it's going to work. Initially, it's going to look exactly like what we did with ellipses. Okay. All right. So let me do. I'm going to set up a little graph here, and then we'll start making some notations. Now, some of the terminology is going to be a little different. Things work out a little different. Okay. All right. So first of all, the center, as you already know, 1, -2. Okay. So I'm going to put the center right here. And then how I start out is as I've said it a bunch of times, very much like the ellipse. Okay. So here, a squared is 9. So a is 3. So and this is under x. So we're going to go left and right 3. Okay, and then in the same manner, we're going to go up and down. B squared is 1, so B is 1. Okay, so we're going to go up and down 1. Okay, and this is where it stops. This is different now. Now, we're not. If this was an ellipse, we would just connect these bad boys. It's not. Don't do it. Okay, so instead, what we do is we use these values to make a box. So I'm going to draw a little vertical segment here and a horizontal segment and a vertical and a horizontal. We use this to make a rectangle. And what this rectangle is for drawing asymptotes. Because we need to know where the vertices of this hyperbola are and how wide to make them. And the asymptotes are the guidelines for that. So I'm going to start at the center, and I'm going to go out through a corner and out through the opposite corner. I'm going to start at the center, and I'm going to go out through the corner and go out through the opposite corner. Okay, so these asymptotes are guidelines for how wide to make the hyperbola. Okay, so start out like an ellipse, and then instead we're going to make a box, and the asymptotes go through the corners. Asymptotes through corners. Okay, so where do you draw the hyperbola then? Okay, well, thanks for asking. Okay, please note that this particular hyperbola starts with x. So the x is the positive term, and since it's the positive term, it's going to go horizontally. And what you do is you actually draw on the box on the left side, and then head toward the asymptotes. Don't cross them. Ooh, that's a little pointy. head toward the asymptotes. Okay, let me fix that because I'm not real happy with how that looked. Okay. Okay, so heading towards the asymptotes, and then you're just going to go right alongside the asymptote. Then do the same thing on the other end. Okay, and in terms of drawing, that's it. Don't draw the top and bottom parts because this particular parabola, or hyperbola, excuse me, started with x. Okay, the x term was first. Okay, let's talk some other terminology and what else do we need to know. Okay, hyperbolas don't have a major axis and a minor axis. They have a transverse axis, and they have a conjugate axis. Okay. Well, the transverse axis, trans means across or change. So the transverse axis is actually, let me switch. Transverse axis is actually the distance from here to here, from vertex to vertex. Okay, so it is the distance or the line, the segment from vertex to vertex. Okay, probably worth noting here that hyperbola only have two vertices. Okay, this point and that point. Okay, so the transverse axis in this case, since this is 3 and 3 from a squared, it is, and it's always going to be 2a, so this is 2 times 3, which is 6, not 9. Okay, the conjugate axis is the other one. Okay, so the conjugate axis is the one that goes the other way. Well, this was 1 and 1. Okay, so this is going to be 2b, so 2 times 1, which is, you guessed it, 2. There's really only one, well, the vertices we could do, I mean, that's not hard. Vertex, start at the center, count 1, 2, 3 to the left. So that's going to be -2, -2. And then the other one is going to be, again, starting at 1, -2, go 1, 2, 3 to the right. So 4, -2. Okay, now, so that now really the last thing that we have to do is the asymptotes. We need to write the equation for each asymptote. So we're going to write the equation for these red lines. Now, I would highly, highly, highly recommend working with the equation in point slope form. Now, I know many of you fight me on this, but this form feels very magical right now. Because this form, I can use any point that's on the line, and the easiest point to use is the center. So I already know that the center of this bad boy is 1, -2. Okay, so I'm going to do 1 minus -2 equals slope times x minus 1. And then the slope, we can count off the graph, but watch this. If I start at the center and go to a corner, I would go up 1 and over 1, 2, 3. Well, 1 and 3, that was just A and B, or B and A, depending on which way the A is, which one's which. So the one that's vertical, remember slope is rise over run. So the one that's about y, change in y over change in x. So we went up 1 and over 3. So the slope for this guy is 1 over 3, or I'm sorry, yeah, 1 over 3. The slope for the other one will be -1 over 3. So I can actually write both of these by saying plus or minus. So that's both asymptotes. I know most of you are saying, all right, what just happened? Okay, now let me point out one other thing here, and then we'll do another example. Okay, let me pop back up to the top. Notice the x minus 1 here. Notice the x minus 1 here. Let it digest. Notice the y plus 2. Y plus 2. I know it's cool, isn't it? The vertical change from the center, we counted up 1. The horizontal change from the center, we counted left and right 3. Yeah, that's it. Okay. All right, let's do another one. That was so much fun. Okay. Now, there will be problems where we're going to have to go backwards. It's just not going to happen in this video. We are going to do this example and then we'll be done. The one thing I did leave out on the last example was finding the foci, and I'm not going to sweat it on that example. We'll just do it in this example. Okay? All right, so standard form. Now, obviously, and you knew this was going to happen, this is not standard form. So what I need to do is put it in standard form. And it's very, very much like the ellipse. The only thing that we have to watch for is when we factor out a negative, we have to be careful about signs. Now, quick little recap here, okay? Not a parabola because I have both x squared and y squared. Not a circle because the coefficients for x squared and y squared are different. Not an ellipse because the sign for the two x squared and y squared terms are different, okay? So if the signs for x squared and y squared are different, automatically hyperbola. All right, so here we go. Get x's and y's together. Now I'm actually going to have my y's come first because they start out positive. Okay, now sometimes they will change sign in the process of doing this, and that can happen because if the number over here ends up being negative, when you divide by that negative, everything will switch around. So don't freak out if that happens. It can happen, and it's no big deal. Okay, and all right, so minus 9x squared minus 54x. I'm going to add 281 to both sides. Okay, I'm going to factor out the coefficients for the squared terms. So 25, leaving some room so I can complete the square. All right, this is the spot I warned you about. So every time when you're doing a hyperbola, you're going to be factoring out a negative, and so you need to be careful when you're doing that. Okay. Okay, so again, this is positive because when I factored out the negative, I had to take the negative out of there and out of there. Okay, so if I redistribute, that should give that exact same thing I had back. Okay, all right, so just a reminder there. Completing the square, you're probably getting really good at this. Half of -1 is -1, or half of -2 is -1, squared is 1. What did I really add? 25. Okay. Half of 6 is 3 plus squared is 9. And so that means on the other side, minus 81. Again, be careful with that sign. Okay. And let's kind of buzz across here. 25 y minus 1 squared. Started right plus. I'm in ellipse mode, and that's not an ellipse. Equal 225. Okay. And let's do a little dividage. A little division, just making up words over here. And hopefully, like back with the ellipses, stuff will just kind of divide out very nicely. And I believe that is 9. And it's real common for these to kind of trade back and forth, probably because we use, cute numbers to make everything easier so that you can focus on the task at hand and not get all wrapped up in scary numbers. Okay, all right, I'm going to go ahead and do some graphing now because that just helps me understand what's going on. Okay, all right, so let me pull that back down. There we go. The center is at, so be careful. What's with x is the x. So here's the x value, -3 and a positive 1. Okay, so -3, 1. Okay. Okay, so -3, 1. Okay, so this is the center. Now, I don't know if you hear the racket out in the hall, but there's a little bit of excitement going on. I don't know what's going on. All right, this is with y, so we're going to go up and down from the center. 1, 2, 3. 1, 2, 3. Okay, and the same idea, we have to go left and right, and again, this is left and right because it's under the x, so we're going to go 5, square root of 25. And 1, 2, 3, 4, 5, and now it's really tempting to connect. Okay, so my scale is totally jacked up. Oh, that's pretty goofy. All right, I'm going to just kind of adjust things a little bit here because this looks a little out of balance. Okay, because I'm winging it here. All right, so we'll put that about there. Okay, so again, it's not an ellipse. we need to make a box. Now you can make it dotted, you can make it solid. Just understand the box is really here just to guide us so that we know what's going on. And now the asymptotes need to be dotted, and these corners, these opposite corners should be in alignment with each other, and if I was on a grid, they'd be much better. Okay, so now the magic question is, does this go left and right or up and down? And I need to remind you the thing to look for is what term is positive. So if the y's are positive, that means it's going to go up and down. Okay, so what we do is we find a little spot on the box, on the box, and then kind of head for the asymptotes. Try not to touch them, but you want to get right along close. What you don't want to do is, sometimes people don't want to touch and they do this. Okay, if you're going to do that, what's the point of the asymptotes in the first place? Okay, so yeah, don't do that. You need to, put it on the box and then head for the asymptote. I'm not going to get out a protractor, compass, or ruler or whatever to measure, but what I'm saying is it's got to follow the right shape, and that's the whole point of the asymptotes, is to establish what shape, how wide, how narrow it's going to be. Okay, all right. So as we're looking, the graph is done. As we're looking for the other information, all right, vertices. Okay, so this was at -3, 1. I went up 3, so it's going to be -3, 4. And I went down 3, so it's going to be -3, -2. So you can either subtract or just count. I went down 3, so here's 1, 2, 3. Now I'm at that point. That's a vertex. Okay. All right, so let's do the asymptotes. Now, the cool thing about this is, again, it's going to follow y minus, well, it's whatever is right here. It's y minus 1 equals x plus 3 over here. And the only catch is I need a slope. And remember, slope is rise over run. So rise, well, it rose 3, and it ran 5, and it went both up and down. So those are the asymptotes. Okay, we got one more thing to do and we're out of here. Okay. And that is foci, the focuses. Okay, now as I told you, we're back to Old Faithful. Okay, so c squared equals a squared plus b squared, or a squared plus b squared equals c squared, same thing. So c squared, c is the distance from the center to the focus. So 9 plus 25 is 34. That's c squared, so c is going to be positive or negative square root of 34. Okay, so again, that's the distance from the center to the focus. So foci, if you recall, we talked about this before, are always inside the curve. Okay, so since this particular hyperbola is oriented up and down, from the center, we're going to have to go up square root of 34 and down square root of 34. So that means we're going to be doing something, and again, the center was at -3, 1. So with the y value, plus the square root of 34 and minus the square root of 34. Those are the foci, the focuses. Okay, and just one little confirmation. So if you actually type that into the calculator, this ends up being -3, -4.831, -3, 6.831, and so -1, 2, 3, 4, almost 5. So yeah, about right there. And 6.8, so this is going to be 1, 2, 3, 4, 5, 6, somewhere up here. And again, part of that's I have scale issues going on with my scary graph here. Okay, so inside the curve, and then the wider the curve, the farther away the focus gets. The narrower the curve, the closer the focus gets. It's just, I don't know, it's cool. So anyway, this is the last of the conics. Now we will do one more video after this that'll be kind of a mishmash. So it'll probably be 4 examples, probably one of each or something like that. Also worth noting that we did not do any examples in here that are backwards. It'll work similar to what happened with ellipses, but we will work examples like that in class or otherwise. So thank you for hanging on, and we'll talk to you later. SanfordFlipMath, bye.